All right, let's go over rice tables today. Let me get to my notes. All right, so rice tables. When we use rice tables, what we use these for is when we have some information but not all of the information to figure out our K, or to figure out concentrations at K. So what we're going to do is we just look at the equation. It says a 1 liter container holds 1.06 moles of H2 and 1.57 moles of CO at a temperature of 162 degrees Celsius. At this temperature, the following reaction occurs. After equilibrium is established, analysis shows 0.2 moles of CH3OH in the container. Calculate the concentration of carbon monoxide and hydrogen and RKC. Okay, so what we need to do is we're going to start out with a rice table. In rice tables, you have to either use concentration, they're good for concentrations, or for pressures. So we have to use molarity or pressures. So what rice stands for is R. And every time I do one of these, this is exactly how I write. I put R, and R is my reaction. So that is this right here. So I just go ahead and I rewrite that. 2H2 plus CO, CH3OH. Rice tables, you can't use them for solids. If there's a solid present, then it's not part of the rice table. You write it down and you just exit out. So gases. All right. So we need to find concentrations at equilibrium. So what we're going to do is we are going to start with, we have our R, now we need our I. I stands for initial concentration. So when they put all of these things into the flask, what is the initial concentration of our reactants, or before any reaction even occurs? So H2, what is our concentration? They've given me 1.06 moles, but I need to be in molarity, and it's in 1 liter. So 1.06 is my initial concentration of my H2. My initial concentration of my carbon monoxide is 1.57 moles in 1 liter. So that would be 1.57 molarity. The initial concentration of my CH3OH. Nothing's been made of it, so it is 0. It initially is 0. So we have Ri. Next is C. Change. How does it change throughout in the to get to equilibrium? This is going to come from your stoichiometry. So this comes from your coefficients. So our change in H is going to be 2x. We don't know how much it changed. And it's going to be a minus 2x because it's going to make some product. For the carbon dioxide, it's going to be a minus x. And for the CH3OH is going to be a plus x. And then we get to E. E is our equation. So that is just 1.06 minus 2x. That's what it's going to be for H2. For CO, it's going to be 1.57 minus X. And for CH3OH, it is going to be X. So our goal is we need to solve for X. So let's go back to our equation, our problem. It says that after equilibrium is established, analysis shows 0.20 moles of CH3OH in the container. So I know when we reach equilibrium that we have 0.2 moles per liter of CH3OH. So that means X equals 0.2 molar. And now we just plug that in to right here. 1.06 minus 2 times 0.2. 1.57 minus 0.2. And so we solve for those concentrations for H2 and CO. So put it in your calculator and solve for those. 1.06 minus 2 times 0.2, 0.66. 1.37. Okay, that's not good enough for the AP. You can't just leave it there. What you have to do is you have to say the concentration of H2 is equal to 0.66 molar. The concentration of CO is equal to 1.37 molar. And then the last part of our question says calculate Kc. So Kc is going to equal concentration of CH3OH over the concentration of H2 squared times CO. And now substitute your numbers in to solve. So always start with that equilibrium expression, and then go in and solve. So we have for ethanol 0.2. For H we have 0.66 squared, and for CO we have 1.37. So what do we get that Kc equals? Kc should equal 0.2 divided by 0.66 squared divided by 1.37. 0.335? 0.335. And our units are? No units. Question on a rice table. We're going to use these for the next 7 weeks. It's just going to be, your change is going to be X. And if it's going away, it's minus X. And if you're making it, it's plus X. And then the coefficient that's with your compound is what goes with your X. Okay? So let's do another one. This time we're doing pressure. So this is the question that we had crossed out yesterday. We're back to it. No, it's the next question. Oh, hold on. Is it not there? Oh, it's out of order, isn't it? I crossed it out. There it is. Yeah, it's number 2. So let's go to number 2. A vessel initially has partial pressure of NO equal to 0.526 atmospheres and partial pressure of Br2 equal to 0.329 atmospheres. At equilibrium, the partial pressure of Br2 is 0.203 atmospheres. Calculate Kp for the reaction. So I just go ahead and start with my Rice table. Just go ahead, RICE. Our reaction is already there, so we really don't have to rewrite it. I, what's our initial pressure of NO? It's 0.526. Initial pressure of Br2 is 0.329. This is before we make any NOBr, so Br is 0. So what's our change in NO? Minus 2x. Br is going to be minus x. And the next one is going to be plus 2x. It's not always going to work out this way where it's minus, minus, and then plus. Sometimes we might be working the other way. We might be shifting back. So make sure you're reading your question and seeing what's going on. It just happens that this is how it is. So then we have our E, so 0.526 minus 2x. And then we have 0.329 minus x. And then we have 2x. At equilibrium, the partial pressure of Br2 is 0.203. So we know that 0.329 minus x is equal to 0.203. So we need to solve for x there. One 0.126.
Don't we divide it by 2?
Not for BR. I'm looking just right here at BR. So 0.329 minus x is going to be equal to 0.203. So x is 0.126. And now we can plug that in to our other two expressions, or other two equations, to solve for those concentrations. So 2x is equal to 2 times 0.126, which gets me 0.252. And this is 0.526 minus 2x is going to be equal to 0.274. Okay, just finding that is not good enough. Oh, it doesn't ask for the concentration. So we know our concentrations. So it doesn't ask us what is the concentration. So we don't have to put that or what pressure. We don't have to put that the pressure of CO is whatever. It hasn't asked us that. It just wants us to solve for Kp. So write your expression. Kp is equal to the pressure, open parentheses pressure, of NOBr, close parentheses squared, over pressure of NO squared times the pressure of Br2 to the first power. And now we can plug in NOBr was 0.252 squared over 0.274 squared times 0.203. .17 equals our KP. Questions on that?
Don't we have to put in how you put in for that other one?
What?
Don't we have to do like concentration?
I did not do it. I mean, you could put it there, but they did not ask for it, so I didn't put it there. They just asked for KP. All right, let's do another one. So we're going back to problem number 7. Following reaction occurs at 298. If 2 moles of HI are placed in 1 liter container and permitted to react at equilibrium, it is found that 20% of HI has decomposed. Calculate KC and KP. So, again, start out with your rice, R-I-C-E. R is 2HI. I2 plus H2. Initially, we start out with 2 moles of HI per 1 liter. So we start out with 2 molarity. Okay, so this would be minus or plus 33.3x minus 6.66. And now we have our A, B, and C. So we go to our quad form, go to your program, and run your program. So A is 1, B is 33.3, and C is negative 6.66. And we get 2 numbers. We get 0.199 and we get 0.3 or negative 33.5. One of these makes sense, one of them doesn't. A negative does not make sense. So our X is 0.199. So now what we can do is we plug this in up here. So the concentration of PCl3 is equal to the concentration of Cl2, which is equal to X, which is 0.199. And then we solve for PCl5. Is 0.2 minus 1 or 0.199. So 0.00100 molar. Is everybody good with that? Everybody?
We had to write anything about them being at equilibrium, like a little EQ.
No, because it just says calculate the equilibrium concentration, so they're going to assume that that's that. Any other questions? Do you guys need me to do one more, or you guys are done with lecture?
Unless it gets harder.
The other one is just like what we just did. It's the quadratic's the ones where it's going to get really hard. But if you have the quadratic solver, and every one of you will have, I mean, if you'll borrow one of these on the AP exam, so you should have one of these on the test. What'd he say? Were you talking to me? No? Okay.